So next up, we'll have Donnacha talking to us about hyperfunctions.
Hiya. Thanks very much. So this is joint work between myself and Nick Wu. I realized on the way over here today that I'd accidentally dressed like Steve Jobs, but unfortunately I'm not going to be introducing the iPhone or something. It's just going to be hyperfunctions. So what is a hyperfunction? Subject of this paper, it is a type, this one here. So it's a recursive type. A hyperfunction, I denote it with this kind of weird-looking arrow here. From A to B is a function that returns a B and takes a hyperfunction from B to A. Okay, this gets a little bit clearer if we expand out the definition one level here. So notice that the order of arguments to the hyperfunction flips on the recursive call. And if we go even one layer more, so notice that all of the B's here, so it's going to be an infinitely left-nested thing, and all of the B's are going to be in positive positions, so it's either going to be returned or to the left of an even number of function arrows, and all of the A's are in negative positions. So in some sense, a hyperfunction takes in a bunch of A's and produces a bunch of B's, kind of, right? Yeah. There are a lot of different ways that you can kind of develop an intuition for hyperfunctions. We're going to go through a couple of them, but noticing the polarity of the A's and B's is handy. Right. So, first of all, just in terms of the definition itself, it's an infinitely left-nested function. It's also really related to continuations. In particular, we can notice that the standard Haskell definition of the continuation monad, when the two arguments of a hyperfunction coincide, it's the same as the fixed point of that continuation monad. So Kant there is just Haskell's Kant monad. The other interesting thing about it is it shows up all over the functional programming literature. So all of these papers have types in them that end up being equivalent to the hyperfunction. And they all actually do similar jobs. So they all seem to show up whenever continuations and concurrency get combined. Okay, so what I want to do first is just go through a few of those examples of where hyperfunctions have shown up in the literature. And then so we can develop an intuition for the patterns that give us hyperfunctions. So the first place is in trying to fuse zip. So Haskell performs list fusion as an important optimization, or GHC Haskell does. And this is an optimization that applies to list functions like map, filter, and concatenation. And the basic idea of it is to remove unnecessary passes over lists. So this is a kind of a classic example of one of the optimizations it performs. Those two expressions are equivalent. List fusion will rewrite the left-hand side expression to the right-hand side one, right? So map F after map G is the same as one map where you use the F after G. The way it works is we rewrite all list consumers to a common form that uses this fold_r function. And then we have some rewrite rules that apply to fold_r. And good producers is the other side of the thing. So if you rewrite it to fold_r, it's a good consumer. And then that can interact with good producers in a way that eliminates the intermediate passes. So zip initially was thought to be the exception to this rule, right? Like we can apply map, filter, and concatenation, we can fuse them away. Zip seems a little bit more difficult to do. So this is just the definition of the zip function. Maybe it's a little bit more helpful to see an example there. So it just takes two lists and it combines the elements pairwise, right? Yeah, so while it is possible to fuse one of the two arguments to zip, and while it's possible for zip to produce lists in a well-behaved way, it's very tricky to see how can we make this fuse on both input arguments. So the solution to this problem was presented by Launchbury et al. In the paper that also coined the term hyperfunctions. Right? I'm not going to show you their full solution here, but I am going to show you just one of the the steps that you can do if you try and get to their solution yourself. So what we can try to do is fuse zip ourselves just by blindly applying, whenever we see a pattern match on cons and whenever we see a pattern match on nil, we're just going to replace that with full-dar, right? So we'll grab the zip x cons x's clause and we'll try and put all of that into the 3 dots for full-dar there. There's a little bit of ingenuity that you need to apply here, but if you keep going with this, you will eventually hit an interesting type error. Unfortunately, you don't get this exact same type error in modern GHC. It gives you something a little bit more probably practically useful, but for our purposes, this is quite cool, because this type error that we're presented with here, when we try and fuse away zip, is GHC telling us that it can't unify the types T0 and then this thing on the right-hand side, T0 to whatever, to whatever, to whatever, right? But even though GHC can't unify the types, we can. We can just go to that place where it has that pesky not equals and stick an equals in instead and put a new type on the left, and then we have a type that satisfies the inequality. So this new type zip, if you see the definition of it, it's the same as the right-hand side of the type error above. And this zip type is a hyperfunction. So this type is an instance of the pattern that we saw on the first slide. So this is our first example of a hyperfunction. So another one came in an email to the types mailing list containing an algorithm for breadth first traversal that included this type on the top right there. This is from Martin Hoffman. And the interesting part about this algorithm was the fact that this type is not strictly positive, and there's some interesting implications to on the theory side for that. But for me, what was interesting is that this is another hyperfunction. So this type doesn't match precisely because roux contains an extra constructor, but the structural similarities are completely there. The difference is really superficial. So this is another example of a hyperfunction being used to do something quite different from what we saw earlier. And this is actually the first hyperfunction that I was able to find anyone using. So the other example that I have is in optimizations of coroutines libraries. So coroutines libraries like pipes in Haskell let you write kinds of programs where yield 1, yield 2, yield 3, and that gets converted to a program that iterates through 1, 2, and 3 and returns those. And then you have another coroutine which awaits them, and you can join them up and so on. If you write these things in the direct style, they can be quite slow. It's very easy to accidentally write quadratic code in your implementation of coroutines. And so Michael Spivey wrote a paper on how to optimize, in particular, the API provided by the pipes library. The thing is, the normal optimization that you would want to apply here is you would want to CPS encode it. You'd want to write the whole thing using continuations. Except it's really difficult to write merge in this case. And in fact, if you do it initially, it seems impossible. It seems like you're not going to zip two coroutines together. Yeah, the problem is merging two coroutines in parallel. A core component of Spivey's solution involved these two types, incont and outcont there. And would you be surprised to see that those are actually hyperfunctions yet again? So this is another example of hyperfunctions in the literature, and we have a few more here. So this is a paper on transducers, where hyperfunctions were used in the underlying representation, or to be specific, the underlying representation contained types that were equivalent to hyperfunctions. This paper implemented algebraic handlers for the pipes library, and in it, these two types were used, which are, again, instances of hyperfunctions. In fact, these are equivalent to the incont and the outcont that we saw in Spivey's example. So why do we care? What's the point of noticing all of these different things in the literature? So it seems like there's a common pattern here that whenever we try and CPS encode an algorithm that performs parallel merging, we have to come up with this hyperfunction structure. And secondly, it is a real headache to figure out how it works. It's a weird looking type. Programming with it is very difficult. Very often when I would come across an example of a hyperfunction in the literature, the authors would remark, by the way, this was horrible to work with. This was really difficult to figure out. Also, the examples I gave, I think that to the best of our knowledge, we are the first people to notice that they actually use the same underlying pattern. Okay? So there's this pattern out there in the functional programming world that is very, very tricky, very difficult to understand, and people don't recognize that they are struggling with something that has already been worked on in other places. So my goal with this paper is to try and raise the profile of hyperfunctions a little bit so that people can recognize when they might be applicable to their problem, when they might be usable in their use case, and also maybe give a little bit of a framework for and a toolbox for working with hyperfunctions. So let's do that now. So a lot of the work on building an interface to hyperfunctions has been done already. So hyperfunctions themselves form a category, and there are a bunch of other handy combinators you can use to work with hyperfunctions. So we have the interface up there on the top right. So you can compose hyperfunctions. There is an identity hyperfunction. That triangle thing. You can treat hyperfunctions like a stream, or you can push functions onto the top of the stream. And on top of that, EdCommet's hyperfunctions library is fantastic and has a huge amount of really, really useful combinators for working with them. Our paper contains a bunch of worked examples on using hyperfunctions to implement functions. Things like comparison or subtraction on church-encoded natural numbers, the zip example, I think another example as well. So that should also be helpful. Yeah, so I want to emphasize the cases where I think that hyperfunctions will come in useful to programmers. So when you're programming, you encounter a problem, when should you be thinking about maybe hyperfunctions are the thing that I need to employ? So we've seen that they're useful at the intersection of continuations and concurrency. Broadly, if you have some kind of program or some structure that you're working with that is encoded as continuations, and you want to communicate between two processes in that thing, or transfer control between them, then hyperfunctions might be what you need to employ. Very narrowly speaking, if you have two continuations encoding and you need to interleave them, it's pretty likely that hyperfunctions will be useful in that case. The examples that we've seen so far are that somebody tries to encode a structure using continuation passing style for performance reasons, and one of the functions in the structure needs to be done in lockstep, and then they discover, oh, this is really difficult to do, and that's where the hyperfunction comes in handy. Great. So now I want to talk a little bit about the theory of the type itself. So the first thing is hyperfunction as a type is quite weird. It contains recursion to the left of the function arrow. It's also non-regular, So the type parameters flip on every recursive call. So for the first of those reasons, it's not admissible in set theory. The cardinality of this type is all over the place. You don't yet get to use the traditional tools you might want to for talking about the theory or the foundations of this type. Especially annoying for me, it's not admissible in AGDA. So because this type is not strictly positive, and in some cases not positive at all, we can't just drop it into AGDA and prove all of the things that we'd like to prove about it. You have to go quite a bit out of your way to make sure that you are dotting your I's and crossing your T's. You have to really check that, this paper presents a handful of techniques of embedding Martin Hofmann's root type that also apply to the hyperfunction type. The second interesting thing about hyperfunctions, I've mentioned that they seem to capture something about the essence of concurrency and continuations. A significant part of the paper is trying to make that notion concrete. And we do so by showing that hyperfunctions can form a fully abstract model of the calculus of communicating systems. So hyperfunctions are at least as powerful as the model of concurrency that's captured by that. This is a calculus that supports non-determinism, parallel merging, and communication. It's a basic standard calculus for these kinds of things. And interestingly, our model is similar to other message passing uses of hyperfunctions in that so the communicator is our model on the bottom right there. The structure of that hyperfunction bears a strong resemblance to the structure of the hyperfunction that we used when encoding zip or when encoding any of the other message passing instances, right? So it actually uses the same principles, the same tricks, and the same kind of structure. On top of that, our implementation is pretty short. You can see it on the right there. I don't expect anyone to understand that, but just note that it's quite compact. It's not a tortured implementation of CCS. It seems to be quite naturally embeddable into it, and as a result, I think it's strong evidence that hyperfunctions do capture something about the essence of continuations and concurrency. Great. So now I want to talk a little bit about some new uses of hyperfunctions. So these are examples, longer worked examples that we have in the paper on how hyperfunctions can let you do some slightly more powerful things. So first is concurrency monad. So there's this classic functional Perl on a poor man's concurrency monad that embeds a concurrent language into Haskell using monads. It's a standard language that has fork, and it's a monad transformer, so you can lift effects from some other monad, and then you get to evaluate them in a concurrent way using some standard concurrency primitives. What's interesting about this paper is if you, the scheduling algorithm in the paper actually performs a kind of a breadth-first traversal over the AST of the concurrent language itself. So what we can do is we can recall Hofmann's algorithm for breadth-first traversal that uses hyperfunctions, and we can try and apply the same thing here. So we can re-implement the scheduling algorithm from the concurrency monad paper using hyperfunctions, and then actually we can go a step further than that and cut out the middleman entirely and build the whole language in this paper out of hyperfunctions entirely. So the language itself is given as that conc type on the top right there. It's the continuation monad wrapped around a hyperfunction. This is a monad transformer in M, so that atom function will lift an effect from M into the conc thing. The main operation that you get in this language is fork, so you can fork a conc computation and let it run, and then of course run at the end, so you can run the thing using all of your desired scheduling back into the underlying monad. Cool. The other example we have is our own encoding of coroutines. So this takes a lot of inspiration from Shivers and Bytes continuation-based transducers. In particular, one of their encodings towards the end of the paper is based on these two types up here. So a channel and then this switch function, which lets you send a message to a coroutine and receive a response. And if you look at that channel type and you look at the recursion pattern that it uses, it should remind you quite a bit of the hyperfunction types that we've been using so far. And indeed, that channel type is pretty integral to our encoding. The benefit that we get from our encoding is that we get this send function. So often in continuation-based encodings of coroutine libraries, you can merge two coroutines, and then all of the yields from one coroutine will get lined up with the awaits in the other coroutine, which is great, but it's quite difficult to implement a function like this, send, where from outside of the coroutine, you actually send a value to the coroutine, and then you want to get back its response and the rest of the coroutine. This is difficult to encode kind of for the same reason that it's difficult to write uncons on a church-encoded list or tail on a church-encoded list. Yeah, you kind of have to turn the continuations inside out. It's very tricky, but hyperfunctions let us do it. And yeah, that's all I have. So thanks very much.
I think we maybe have time for a couple of questions.
Thanks for an interesting talk. So yeah, one of the examples was from my paper on handlers in action, the pipes we implemented there. So it was the implementation we did with deep handlers of pipes was very convoluted, and I can see the connection to hyperfunctions. But if one switches to a different notion of handlers, shallow handlers, or better, some kind of multi-handlers, as in Frank, then the definition of pipes is really straightforward. What's going on there?
I'm not, so a similar thing like that happens actually with fusion. So you can also do stream fusion instead of the fold-R-based fusion. And the stream fusion doesn't run into any of the difficulties with zip. All of that stuff kind of falls away. But it seems like the two things are dual of each other with relation to hyperfunctions. So what I would expect is that the hyperfunction encoding, it's very difficult to encode the zip-like things or the coroutine handlers, but it probably has advantages in other respects, if that makes sense. So the hyperfunction lets you fuse away inductive things, and it's very difficult to do on merging, but I think that in the case of folds, for instance, it lets you keep up your fold fusion machinery elsewhere. So I wonder, is there a similar trade-off, basically?
Thanks.
Any other super quick question? Okay, I actually had one super quick question myself. So you had the library in the, you showed some like library functions in the middle, and you showed you could run a hyperfunction from A to A.
Yes.
Is there a more general way to run hyperfunctions that are not from the same type to the same type? Do you?
Yeah. So.
Sorry, sort of right in the middle.
No, there's no problem. So you get this run type on the top right. So the other main way that you would eliminate out of a hyperfunction is a hyperfunction from A to B. You apply that to a hyperfunction from B to A, and you get a B out. So that would be the most general way of Exactly. Yeah.
Okay. Let's thank the speaker again and move on to the final talk of the session.